In this video, we will be introducing our work, CFCG, Semi-Supervised Semantic Segmentation via Cross-Fusion and Contour Guidance Supervision. First, we will be introducing the background of semi-supervised semantic segmentation learning. Semantic segmentation, an essential task of the pixel-wise classification task, has been remarkably successful with the development of deep learning. However, the training for such a problem is rather a challenge owing to costly and laborious pixel-wise manual labeling. To alleviate this problem, semi-supervised semantic segmentation with the precious labeled data and large amounts of unlabeled data is urgently needed. Under such a setting, how to adequately leverage unlabeled data becomes critical. Recently, approaches based on the combination of consistency regularization and pseudo-labeling dominate semi-supervised semantic segmentation research. Especially, it encourages high similarity between the predictions of perturbation for the same input, but expands confidence prediction map of an unlabeled image to a one-hot pseudo-labels map. However, it still exists some problems. First, supervisions from a single learner tend to be noisy, which causes unreliable network-level consistency regularization. The existing paradigm evolved from a single learner to two learners. Typically, as shown in Figure 1a, a single learner with WS strategy is first proposed. Then, with the advantage of mean teacher, the framework evolves to Figure 1b, in which WS strategy is applied together with two learners. Figure 1c further introduces the symmetric dual student method, where both strongly augmented images and weakly augmented images flow into bipartite learners. It uses the pseudo-label obtained from one network to supervise the other network and vice versa. During the test, only one of learners is used for inference in two learners paradigm. Undoubtedly, ability manifested in the process does not reach the ceiling due to the empirical observation that direct learners merging produces better performance than what is obtained currently. Second, existing pixel-wise confidence score-based reliability measurement causes potential error accumulation as the training proceeds. Figure 2 illustrates the confidence score distributions of pseudo-labels on the VOC dataset. We can observe that it is almost impossible to identify unreliable pixel-wise pseudo-labels via pixel-wise confidence score thresholds, which is widely adopted in semi-supervised. Furthermore, we can also observe from B and C of Figure 1, the confidence map is usually noisy and unreliable as highlighted by the red box. This issue leads to error accumulation as the training proceeds, thus seriously affecting the performance of semi-supervised learning in segmentation tasks. Previous pixel-wise confidence score-based methods struggle with very limited performance gains. We also found that the similarity between error map C and weight map F in Figure 2, where most of the unreliable spatial regions can be identified by the contour map, which inspires us to give our method. To solve above problems, we propose a novel semi-supervised semantic segmentation framework called CFCG, which mainly includes cross-fusion supervision and the adaptive contour guidance module. Our cross-fusion supervision, which neatly blends coherent perturbation, can tap into underutilized knowledge to enhance the quality of pseudo-labels during the training stage and help enhance expressive power during inference. The proposed adaptive contour guidance module introduces the semantic contour for encouraging position relations establishment as guidance to effectively identify unreliable spatial regions in pseudo-labels and accurately mitigates the problem of confirmation bias. In general, cross-fusion supervision first realizes cross-learner attention and fusion for both weakly and strongly perturbed learners, respectively. Then consistency regularization between the two learners is calculated based on the fused weak logits. Specifically, in cross-learner attention, after an element-wise sum operation, average pooling is used to encode the spatial representation of different semantic channels to generate vector A. Then, vector A is fed into different FC layers to generate two attention vectors. In weighted fusion part, generated attention vectors are used to perform optionally weighted fusion for two input features to generate final feature map. Finally, we introduce cross-supervision, which calculates consistency loss between the fused logits of weak and strong flow, respectively. Adaptive contour guidance module gradually applies a contour-guided weight map to re-weight training loss. Specifically, in the first step, as shown in Figure 3c, semantic contour maps are exacted from the pseudo-labels by the Laplacian group. In the second step, image processing operations, including Gaussian blur and normalization, are injected into this semantic contour map to produce the weight map. Finally, we use the weight map as the coefficient of cross-entropy loss to guide the model to leverage spatial information and distinguish the noise in pseudo-labels. Compared with direct multiplication, we take into account that the learning ability of network in the early training stage is not enough, so we adopt a progressive strategy to gradually introduce the knowledge of semantic contour. We compare our method with some recent semi-supervised segmentation methods, including CPS, U2PL, UCC, and PSMT under different partition protocols, using the same architecture and partition protocols for fairness. Table 1 and Table 2 show the comparison results on Pascal VOC and Cityscapes. We can see that over all the partitions from 1/16 to 1/2, with both ResNet 50 and ResNet 101, our method without fusion inference and with fusion inference consistently outperforms the other methods. In conclusion, we propose CFCG to tackle the semi-supervised semantic segmentation task. Concretely, cross-fusion supervision mechanism can leverage multiple learners to achieve stronger expressive power. Adaptive contour guidance module introduces the semantic contour for encouraging position relations establishment as guidance to effectively identify unreliable spatial regions in pseudo-labels. Thank you for watching this video.